All right, this is the, let's see, this is section 3.4, linear and angular speed. Let's see. Okay. Well, maybe a little bit more. Okay, that's better. So this section talks about, this is all about a point moving on the edge of a circle. And we have two ways of talking about its speed. Either the distance it travels, like the distance, the typical the speed you're used to, like maybe like a satellite orbiting the planet. It goes at a speed in normally miles per hour. So that's our linear speed. It's the speed going in this line, this curved line. We can also talk about how quickly the angle it's rotating through, how quickly that angle is changing. So that's our angular speed. So that's it for this section, talking about these two different types of speed and how they relate to each other. So you see, any point moving around the edge of a circle goes through an angular speed. Right, the angle it's moving through goes at one speed, and intrinsically related to that is how far this distance is it's going along the edge of the circle would be. So I've got some circle kind of haphazardly drawn here. It's my giant circle here. So again, any point traveling around that will have both a linear speed, which is this distance it's traveling, divided by the amount of time it's gone, and also whatever angle is traced out during that time, however many radians that goes through. So, linear speed. Now that I drew this giant thing, I'm just going to have to erase it. So linear speed the variable we're going to use for this is v. When you take a physics class or a calculus class, you'll see v used all the time to talk about velocity, but that velocity they're talking about is almost always linear. It's the linear speed you're going at. And it's easy enough to do. We take the distance we've traveled and divide it by the amount of time that takes. So divided by time. What variable do we use for distance around the edge of a circle? Well, if you look at 3.1, you already know that whenever you trace out some angle in a circle, the distance around the edge of that circle, around the circumference of the circle that you move, is called s. Yeah, that's our arc length s. Okay. So the linear speed is just that arc length, so that distance you've traveled, divided by the amount of time it takes to do that. So then your angular speed it's the angle that you've gone through in that same amount of time. Now the variable we use here is omega, or this weird looking W thing. Okay. And it's just the angle you've gone through divided by the time. Now, in keeping with our radian units, from here on out, we're just going to be using radians. So this angular speed doesn't have any unit other than radians. So no, we're done with degrees. I'll probably still mention degrees. In fact, you'll definitely have some problems that are done in degrees. You need to know that when you're dealing with this speed, you're going to have to convert that to radians. We've got some other formulas about converting between linear and angular velocity, which I may spend some time on. Probably not. No, I will. I will talk about those. But that relationship always also requires this to be in radians. So this thing's got to be in radians for this stuff to work. Okay. So what type of problems do we have here? Let's see. So here's a nice example for you. Now, some of the homework, the first few homework problems I gave you are pretty straightforward. They're going to give you some of these variables and ask you to solve for the other. I mean, they may literally just say the arc length is 5, the time is 6 seconds. What is the linear speed? What's the arc length divided by the linear, the speed? So that would have been what? 5 divided by whatever I just said, 6 seconds? 5, 6. I guess I'd have to have some kind of unit up here, like 5 inches for 6 seconds. So the first few problems should be really easy. What I want to talk about is the word problems, because that's where people struggle with this stuff. So for example, let's see. Find the angular velocity of the minute hand of a clock. Okay. Or find the angular speed of the minute hand of a clock. Okay, so where were we? Find the angular velocity of the minute hand of a clock. So if we've got a clock assuming the minute hand, we're just looking at the minute hand made by this circle, find the angular velocity of this minute hand in speed per minute. So the question is, how far is this thing going to move? What angle is going to go through in 1 minute? Well, in order to answer that question, so it's the angular. Well, what is that angular velocity? So all we have to figure out, well, we got to know our definition. This is the angle we move through divided by a given time. So let's look at it. And we're looking at a minute hand here, right? So we can look at a few different rotations. We could say in 1 minute, how far does it go? How far does that thing move in 1 minute? Well, heck, I don't know. some number of degrees, right? Well, we don't want to work in degrees. We're working with this unit. Let's measure the radians. We could say that we move through some fraction of 2 pi radians. That makes sense to me, because in one circle we go through 2 pi radians, right? 1 full revolution. In our minute hand, if it goes through, 1 full revolution, we've gone through 2 pi radians. So we could say, how far does it go? How long does it take to get through 1 full revolution? That's one way of thinking about this, one way of approaching this thing to solve this problem. We could say in 1 minute, since we're talking about the minute hand, we know that we could choose our unit of time and say, well, how far does that go? How many revolutions does it go through in 1 minute? Now that one, well, how many revolutions? How far is 1 full revolution? Or how many minutes does it take to go through 1 full revolution? Since it's the minute hand, it takes 60 minutes, right? So in 1 minute, how many parts of the revolution did it go through? It went through 1/60th of a full revolution. Right. So it takes you 60 minutes to make one full revolution. Then in one single minute, it's gone through 1/60th of a revolution. Also, I could say, how many revolutions does it go through in an hour? Maybe that's how you wanted to approach this. How many revolutions does it go through? Well, in 1 hour, my minute hand goes through, well, let's see, in half an hour it goes down to 6. Yeah. In 45 minutes it comes back up to 9. And in a full hour it's gone through 1 revolution. So I could say, how much does it go through in 1 minute? It goes through 1/60th of a revolution. I could say in 1 hour it goes through 1 revolution. So I've got a few different ways of approaching this thing. Eventually we're going to have to convert this thing into radians per some amount of speed. So what angle has it gone through? One way or the other, you have to know that throughout this entire revolution, it's gone through 2 pi radians. So once we have that, figuring out the time it takes to go through that, well, we've already done it. To get through a full revolution, that took us either 1 hour, if you want to think of it this way, or it's taken 60 minutes. So what is our angular speed? We've got the distance we travel, 2 pi radians, divided by the amount of time it took us. We could say it had gone 2 pi per hour. So that would be one way of writing our angular speed. We could also have said we go through 2 pi radians every 60 minutes. And that one we would have to reduce a little bit. That one we cancel out our 2 with a 60. We get pi over 30 radians per minute. So a little bit of discussion about where I could start the problem, and then eventually we have to bring it back around to our angle and the amount of time it took. And then we could write our angle either in radians per hour. All right, so next up I want to talk about the relationship between linear speed and angular speed. And I want to do this by looking at this wonderful comic from Calvin and Hobbes, where Calvin is getting messed with by his poor dad. So his dad says, "Playing a record, Calvin, I'll show you something interesting. Compare a point on the label with a point on the record's outer edge. They both make a complete circle in the same amount of time, but the point on the record's edge has to make a bigger circle in the same time so it goes faster. See, 2 points on one disc move at 2 speeds, even though they both make the same revolutions per minute." This is a fantastic comic. It's a great way to troll children. Just everything about this is great. And of course, Bill Watterson, Calvin Hobbes, both fantastic. Okay, so looking at a circle, this is our record. We've got the label on the inside of the circle. Those of you who aren't familiar with records, I imagine a lot of you are. We've got the record is spinning around this central point. We've got the label, the artist info right here in the middle, and then the part that actually records the music. And they're all fixed on one disc. So we're talking about 1 point here on the outside of the circle, and 1 point here on the outside of the label. And this thing is moving, and just like Calvin's dad says, this one on the outside has to be going faster because it's going a greater distance. And you can see, just looking at this, this is a large distance, and this one inside, this is a much smaller distance. And just like when people are racing, they want to stay on the inside of the track because a smaller distance, a lot of times that's where you want to be. As opposed to outside, you have to go a longer distance. So, how can this be true? Poor Calvin, he can't figure it out. Fortunately, we can. So we're gonna talk about that now. So, what exactly is going the same speed here? Is it the linear speed? Clearly not. He's going a larger distance. You know, the point on the outside of the circle is going a larger distance. That has to be a faster linear speed, just like his dad says. And on the inside, it would have to be going a slower linear speed. Where he's messing with Calvin is the angular speed. The angular speed does have to be the same because, you know, any point, like I move this point from here to here, I've gone through some angle, theta. This point also went through that same angle. So the angular speed has to be the same. The linear speed does not. So how are these linear speeds related to each other? It's actually really simple. I've got the algebraic way written here for you, kind of outlined what's going on. But the length is proportional to the radius here. As the radius increases, the linear speed increases. So the rule here is that the linear speed is linearly proportional to the angular speed. A simpler way of saying that is it's r times omega. Nice omega there. So as the radius increases, the linear speed, which is the radius times the angular speed, that would also have to increase. So that's a nice way of memorizing it. If it helps you, as the radius increases, the linear speed has to increase. So a great visualization of this rule, which is going to be immensely important for problems like this that involve two circles with the same angular speed. Now, actually, I don't think my math lab had any great examples. Your textbook is full of these things. For some reason, my math lab didn't have any great ones. If I find any, I will throw those in there. But I didn't see any my first time through, which is very disappointing. But this is a really common reality of engineering, where you have the same angular speed, and we want to use that to translate. We want to change linear speeds doing this, using this. You know, sometimes you'll have one big gear, right, and on its axle there, you know, attach that same hub, going to that same axle, we have a smaller gear that allows us to change the linear speed of our motion. That's actually a really common type of engineering problem. Again, no fantastic problems for that in my math lab for some reason. So unfortunately, you get to miss out for that. All you get is this beautiful example from Calvin's dad. I do have a great example going the other way, which I'll do for you right now. Okay, so this is our example I wanted to look at. This is similar. This is a similar type of idea to Calvin and his record player, but a little different. So 2 points on the same circle, or two circles that share a hub, you know, they're fixed together for whatever reason. They have the same angular speed, but their linear speed is going to be different. This is a different case where we've got two circles that have their own hubs, meaning they can have different speeds that they turn at, different angular speeds, but they're connected by a chain or a rope. So these are my terrible gears. They look really bad, but these are supposed to be gears here. Like in a bike, you have some big gears back here, some little gears up here, or vice versa. So we've got this problem here. We want to talk about how these different linear and angular speeds relate to each other. So in this example, I've got my rear gear here has a radius of 15 centimeters. My forward gear has a radius of 8 centimeters. And they tell us a little bit of information. They tell us that this rear is rotating at 25 rotations in 36 seconds. I don't know why someone would measure it that way. I don't know how they decided to do that. But somehow we've been given this number by a customer or whatever, and we have to figure out some angular speeds for that customer. I don't know. I'm trying to think of a great situation where this would be feasible. But changing between these things, these two things shouldn't be difficult. So first off, the relationship between the rotations and the amount of time, from that we can come up with that angular speed. So the question actually asked me, find the angular speed of each of these two gears. So what is my first one? I've labeled it omega 1 for the first one. Well, that's just the angle I've gone through in a given amount of time. I've gone through 25 rotations. Each rotation is 2 pi. So I've gone through, I'm going to change color here. I've gone through 25 times 2 pi radians. Right? Each rotation is 2 pi radians. I've gone through 25 rotations, and that took me 36 seconds. So I can simplify that. I could cancel out a 2 from each of these. 2 and 36. That leaves me with, on the top I've got 25 pi radians. On the bottom, I've got 36 divided by 2 is 15, 16, 17, 18 per 18 seconds. Or you could say I've got 25 pi over 18 radians per second. So I've got the first part figured out. The question is, how can I relate that to this second angular speed? The way I'm going to do that is using my relationship. I know that these two things have to have the same linear speed. I found the angular speed of that one. From that, I can figure out the linear speed using my rule here. So using that, I can now find my linear speed. So R is, in our case, 15. The case of my first circle there. 15 times 25 pi over 18 rad per second. Okay? And gosh, I could simplify that. I'm just going to multiply that out and leave it as a gross unsimplified fraction. So 15 times 25 is 375. Okay, and now I've got a unit there. My radius was in centimeters. Since radians are not really a unit, I don't just ignore those now. So now I've got this thing in centimeters per second. So now I've got my linear velocity of this thing. So I've got the angular velocity, I've got the linear velocity, but that's the key idea here, is that this has this linear velocity, this has this linear velocity. Those two have to be the same, because whatever point I've got fixed here, moving at this speed, has to be moving along this one at the same rate. Right? They're physically connected along the outside of the circle rather than along that center. So the speed along the outside is the one that's connected, not the speed of the interior angle there. Okay, so now I've got, what I just found here was my first speed, V1. But the idea here is that has to equal V2. So I found V2 as well. So since those are related, I've got, since V1 equals V2, now I've got the linear speed of this circle as well. And from that, I can use this relationship to find W2. So V1 equals R1 times omega 1. Well, then what is omega 2? Omega 2 has to equal R2. Oops, sorry. I can start off with the same relationship here. V2 equals R2 over omega 2. And now I just solve this thing for omega 2. So I divide by R2, divide by R2. And I've got omega 2 is my V2 over R2. So that's really nice. Now I can figure out what I was asked. Okay, so it's just going to be my angular velocity is equal to my linear velocity divided by my radius, that second gear. But what did we say? We said that linear, this is that thing that differentiates this from Calvin's example. Here the linear velocities are the same, not the angular velocity. Okay, so now a V2 is going to be the same. It's going to be that 375 pi over 18 centimeters per second. Okay. So 375 pi centimeters per 18. Oops. Yeah, I'll go ahead and write it there. Now we're taking that and we're dividing it by this radius. We're dividing that by 8 centimeters. So again, just a little work with fractions. This is 375 pi centimeters divided by 18 times 8 centimeters times seconds. Okay, and my centimeters cancel. And I've got 375 pi over, I'm not sure what 18 times 8 is, but I've got this handy calculator. 8 times 10 is 80, 8 times 80 is 64, 80 plus 64 is, I don't know, 144 seconds. So there is my second angular speed, 375 pi over 144 seconds. And we could try to simplify this. I don't think that simplifies. Let's see. 375 divided by 144. Oh, that does simplify just a little bit. So I get 125 over 48 pi radians per second, or just 125 over 48 pi per second. There we go. If we wanted to find that approximation, I'd multiply it by my pi. I get, this is approximately 8.18 radians per second. And that time I actually wrote the radians. I didn't write it here, but there we go. Radians are that great unit we can leave or add in as we want. Whatever's the most confusing, right? That's what it always seems like as a student. So there we go.